So, some backgrounds. This fellow got this very cool thing he's got running. Is a couple years old, but I'm just getting into it now. This is a really cool operation. Now, in essence, the angle is you take your input, right, and it shows that here. So this is your input. You parse a number of tiles. The tiles are n by n pixels wide. So basically what that means is I'm looking at a neighborhood n by n pixels around this this pixel that I've picked. All right, so say for this one, I'm seeing this pattern where these neighboring pixels have these kind of relationships. And so if you if you go through for every pixel in the image, then you can start to see where these relationships exist in the original image. So the idea here is to take that and expand it out into a larger image that maintains these types of relationships between the pixels. Now the really cool thing is that the diversity of different patterns that still fit the constraints established by the initial image. Very, very cool. So basically these pixels that have sort of a blended color that represents a superposition of different possible tiles. So that is a little bit oops. This guy has an implementation in JavaScript that I took a look at. I'm going to be working in C++. Here we go. So I'm looking at the overlapping model, which basically, like here, this is a visualization that was posted later by the same guy. But you can look at the these neighborhoods, right? They've highlighted them in colors here, but how they're repeats of well, I guess this is just showing the set of the input. So yeah, this is colored by what tile that would represent. Now, right, and so you've got your input corresponding to your output. He also had, so this is the demo I'm looking at the code for. He's got it set up so you can draw some pixels, and this is kind of cool. So I say, all right, I've got this set of input pixels. Now, I'm using 3 just because it makes more sense to me, and which, I mean, I think it's cool the way he handled the multiple size neighborhoods. There is a couple things I'm going to change about that, but because I do like the way that I was representing tiles, especially the way he does his rotations and mirroring is not flexible enough to do all 8 permutations. So I'm going to definitely use the way I was representing tiles, and there's no incompatibility between those two things. I went through everything, and it does the rest of his approaches. And see, now I was missing a pretty sizable chunk of, because I had attempted to implement this without really, like, just kind of, I've got the concept, how am I gonna implement this? And I went about it in, I guess, what turns out to be a relatively naive way. The angle was, okay, I parse all the tiles out of an image, and I created these things that I was calling tile dumps, and it's, you know, this is going to be potentially a useful debug tool later, but where the hell is it? I need to organize my shit better. Let me figure out what's going on here. Should make sure this is actually working. Interesting. I guess the default was to have this be unlisted anyway, so I'm able to see it on my other computer now, so very good. So anyway, I've got this input established, and I tell it to generate. Okay, his implementation returns white pixels when there's contradictions, so I'm gonna look at ways to do like a partial collapse or something. Maybe started at a different point or something. It's anyway, neither here nor there. So the game is right. I'm creating this initial layout. Then I want to create some output based on. All right. Let's try and do something more basic. So, right. So we've got the superposition of all the output pixels, right? And as see if I can zoom in here a little bit. As we go through here, we go through this cycle of generate and propagate. Or observe and propagate. So basically, observe is, okay, something has changed. Now I need to remove all the tiles which no longer fit the constraints as established by the collapsed pixels. So, right, I know that there's black pixels here. Well, you know, what does that tell me? How likely is it that, you know, see here, ones that are more green are ones where those tiles say that, or the remaining tiles suggest that there's more potential for a green pixel at this location. So, and this is something that I'm seeing a lot of, is that when you have these more complex inputs, there's a tendency to get kind of locked into this pattern thing. Let me try and explain that a little better. I think I need to, yeah, because it goes into a while loop in this implementation, so I don't think it, I'm not 100% sure. It doesn't really work when you reset the page, or until you reset the page, rather. So we'll do something like that, and maybe that's a little bit okay, well, here we go. So there's a lot of checking in this algorithm. It's basically all checking. So the one part that I was that I wasn't thinking about in the way that this guy was thinking about, right, he's got a pre-computation step where it looks at the sets of tiles that any given tile agrees with and the offset between those tiles. And basically what that is like, all right, if you're going to lay them over top of one another, 0, 0 is with them just fully superimposed one over the other. Now, they could be offset to the x by 1 or 2 or 3, up to, n in either direction, because at that point the tiles would no longer overlap. So the idea then sort of becomes like, okay, I've got this representation. This is what I'm using to eliminate these patterns, I guess, in the output, right? So as I'm rolling back this curve here, I'm seeing more and more contradictions, or rather, more and more established non-relationships, right? So, well, and see here, this has already become more diverse than the, or anyway, you see how this is set up here. Now we see that here, but also down here, because those tiles are also rotated. And like I say, the way that he rotates is not exactly my favorite, and I think I had solved that problem a little bit better in my code. Well, I don't have as general a solution as he does, and so that's part that I'm going to improve in this implementation. But here, well, it's easier if I just show you. So the this is done in my engine thing that I've kind of been using. It's not pretty, but it works, and it has a lot of utilities that are very handy for all this type of stuff that I've been doing. So the okay, I also need okay, so I have some number of maximum colors established. Now, even with this, I think it's gonna not. I don't know. It's gonna be weird because you saw how few colors that was limited to, and the size of the neighborhood that was limited to, and the number of tiles in the input is also a major limiting factor, because that's how many superimposed patterns there are for every pixel in the output. So my solution here was just like, okay, I've got a 9-element array, and I explicitly indexed each one, and that's where I'm going to change to like a vector of vectors kind of a setup, so I can do two-dimensional indexing. Because this being hard-coded at a value of n equals 3 is potentially limiting. And I really do like the way that I'll go through that implementation too. So rotate basically says, all right, I have this established pattern of data in the input. All right, now turn it, right? So, or rather, I guess counterclockwise. So you've got here 0, 1, 2, you've got 0, 1, 2, 3, 4, 5, 3, 4, 5, 6, 7, 8, 6, 7, 8, right? Mirroring is very similar, except I'm looking at the write the mirror image of this. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8. And then it's returning a tile that is the rotated version of it. So the way that I use that is to generate the different tiles. Yeah, here we go. So for every pixel in the image, right, for X and for Y, then I'm going through here and adding a tile that looks like, you know, and this is, I kind of like the way that this was set up. So I have this define set up, and then it'll drop through as many of these as there is. So, right, so 1 counterclockwise rotation, 2, 3, mirrored original, mirrored, 1 rotation, 2 rotations, 3 rotations. So this goes through and generates all of these things, and I like this structure. So, and actually the way I'm looking at it right now, I want to make this rotate function general enough that it just takes an integer type that's going to be this. I did actually like how this was, so probably, I don't know, we'll get there. So the idea here is like, okay, sort the tiles. All right, I thought maybe this next step would be simpler if they're in some sort of order. So I had defined less than operator that compares the data type at the center. And basically what that's doing is going through and saying, all right, the tile's considered greater than or less than based on the index of the color of the center. And the reason I'm using an indexed palette that's up to that size, that's based on whatever size input, excuse me, the number of colors in the image. So let's take a look here. Yeah, so some of my input images, like, I don't know, and this may be totally impractical. I could be looking at this completely wrong, because I don't know. There's so many different relationships to be considering here, and like I say, there's a lot of duplicates. So that's the next step in the input parsing step. But basically, for each one of these pixels, I'm looking at, you know, the neighborhood around it and saying, okay, well, that's a tile. That's one potential relationship between a pixel and its 8 neighbors. Okay, so basically what the previous implementation had right and is, you know, workable, and a lot of this is just going to carry directly over. We'll just look at the same one. This is number 2. Okay, so for that input, and we'll do it in GIMP because it's a lot easier. And the filtering, well, I'll just show you that too. The filtering actually creates some interesting artifacts. The way it does it in the image viewer, it looks solid at different points, and you get some interesting patterns. But anyway, so this is all of the input, right, parsed into a huge set of these, in this case, 3 by 3 tiles. And like I say, this implementation is going to be a lot more flexible, but we're getting there. So this is, so here's an example of rotated input. So this was then just rotated to create this, or vice versa, I guess. But either way, the idea here is then that this 3x3 relationship is potentially, you might see that repeated in the output, but rotated. And so, for example, the one that had the plants that grew here, now it only goes in an upward fashion. So what he did here is symmetry is set to 1, right? Or so maybe it was mirrored as well. But you don't see flowers upside down, right? Because those relationships don't exist. They're not created in the input. So you don't have one where it's yellow pixel, then blue pixels down here, right? You have only the ones where it's yellow pixels and then green pixel below. So that constrains the output pretty significantly. So as we're dealing with this many tiles, we have a lot more different relationships to look at. And so this potentially becomes a hell of a lot of work to go through and check all these things. Because if you think about it, you have for input size n, well, bad to call it n, just, you know, whatever. Just if you talk about it in big O notation, your input image has n pixels in it. Well, you're generating up to n tiles, right? So there's a factor of n. Well, then you've got to sort. Okay, so sorting is potentially, I mean, it's probably not much time, but that scales with the size of the input, of course. And so I haven't talked about this duplicate removal process, but I also established this equality operator, and that's like pretty simple. It just goes through and says, okay, are these exactly the same? And right, and that's erase that tile, you know, the one that's there, and then move back one, because you've eliminated one. Let me think about that. There might be an off by one thing going on here. I've got to look at it more. But in any event, we remove all the duplicates, and then so reports how many distinct tiles are out of there, and like I say, there's this many potential. There's the width times the height times the number of rotations and mirroring combinations that we did. So that generates a lot of potential combinations out of an input this size. So that was actually one of the main considerations of the original one, is that those input images are very small. So you keep the right, this tile set here, this is the set of tiles that you get from the small image of the flowers, right? And so these are all the patterns you see, and this is with rotations. So this and this both exist. So like I said before, the green pixel above the flower does exist in this set, and also in this case beside, because that tile's been rotated, right? And there's not 8 here because this mirrored is this, and this mirrored is itself, right? So vertical symmetry there, and so those are removed as duplicates. Similar situation with the other flowers, right? They were deleted as duplicates. So yeah, this is sorted by occurrence. I was kind of stripping some stuff out So these may not be sorted by the occurrence, but anyway, there's a count for each one that would have been incremented, right? That's because we saw it, and the reason for that is because later during the collapsing thing, you have they call it entropy, but basically you're looking at how likely the different tiles are compared to one another. So if you have, okay, well, so looking back at this implementation, these black pixels, there's quite a large occurrence of these in the output, and that's because there's a large occurrence of that particular tile in the input. And similarly for these, this is a pretty common pattern right here where you've got red and green right next to each other. That's pretty common. So we're seeing where it was picked above all other patterns for this long stretch and for this long stretch and this long stretch. And those are all longer than this input. Would suggest that, you know, this pattern is this long. So so that's kind of interesting. I really don't like JavaScript. I'll just be honest about that. That's just kind of not great to go through, but it was relatively simple. I went ahead and put together yeah, I just put it in a PDF. So his Vec2 class, I don't like the way the rotation is done, because I don't quite understand what he's doing here, and even so, I don't. It's constrained to 4 rotations, and like I say, I really don't quite parse what's the game here. Anyway, I can much more easily see, because the way he uses it is here in the pattern thing. He's generating these patterns, but then marking them as 90, 180, 270 rotations, and then he's going through rows in the pattern. And I mean, I guess it makes sense, right? Because it's basically just right. It is literally just rotating that array. And I'll be doing something similar, I guess, at this point, but having these as like hard-coded things rather than just a 90-degree rotation and a mirroring, you know, by doing those two, I can generate all the others because they're just concatenated. And this step is only executed once, so it doesn't really matter if it's crazy slow. It's really not. This is just the pre-processing. We're still in here. So the way he does his equals, I do kind of like, because it generalizes. Well, the equals is not that big a deal. I can just write an equality operator that does the same thing that I was doing in the other one. But anyway, the agrees function. This is the part that I had missed. You know, does this pattern, right, agree at this particular offset? And again, this is where I really don't like JavaScript, because there's an implicit this, right, which then says, okay, I'm talking about some pattern, right? Anyway, whatever. It's not worth getting into. But the idea is, all right, so does this agree at this offset, you know, for all the pixels? And if there's any violation of that, you're going to return false. Otherwise, those two patterns can sit right over top of one another at that offset. So it's pretty remarkable how close this comes to resembling Sudoku in terms of I saw a video that drew the same kind of a comparison, but basically, when you establish a number in the in Sudoku, you've eliminated that number from some neighborhood around it. And that's basically saying that for all those neighboring tiles or squares, whatever, you've removed all of the tiles that contain a 3 in that neighborhood, right? With offsets that would violate the relationship that there's a 3 there. So that's kind of, I don't know, it's kind of cool. But so basically, yeah, so he's got his vector class, a model class that does the processing, and I actually had called it model too. Yeah, this is all before I looked at this fellow's implementation. I'd written all this, and there was one part that I was doing this step. I was trying to be clever, and anyway, it didn't really get me anywhere. I was doing some interesting stuff with lambdas that Jesus, it's gonna make a liar out of me here. That's yeah. So this part, I thought this part was cool. Thought this was actually very cool. Right. So I was going about this the wrong way. I was going through, yeah, because I was getting a bunch of seg faults when I collapsed. This is the wrong way to do it. Anyway, it just doesn't work. Because it doesn't take into the relationship it doesn't take into consideration the offsets, and if the agreement between neighboring cells. So this has a whole nother layer that I wasn't considering, and like I say, that's why it's kind of saying that this is my approach initially was kind of naive. But so the idea here is, okay. It's just some debug shit because I was confused as to why the hell nothing was working. But so, okay, I collapsed this output cell. That means I picked no, wrong collapse function. I've got 3 different things called collapse, and that's probably not the best way to do it either. So yeah, basically I would just say, all right, somewhere between 0 and possible tiles less size, I pick one tile. That's the new tile. Okay, so that says, all right, clear the tiles, and that's the last one. So market collapsed, and this was not working. I was getting rid of all the cells. Now this, see now, I like the way that this fellow is doing it a lot better. The pre-computation of all the overlaps with the offsets. Because here now, the possible tiles vector. So basically, this remove if this is cool. So this erase function takes an iterator, and remove if is kind of an interesting structure here. Well, so now this isn't right because there's actually a third argument that is possible tiles.end, right? And that's the corresponding iterator to this much of that. Anyway, this is kind of a complicated function you try and use, and I may have been using it wrong, but I think that changing my approach was going to be better in the long run anyway. I'll probably end up using something very similar to this type of code, but this lambda will be different. So basically the lambda takes this, right, the model, and this color, which says, okay, the neighbor function, which was looking at one entry in that initial array. Okay, so anyway, like I say, we're changing how that works. If the tile at that, okay, and the tiles are indexed as well. So the tile number T, if the color doesn't match the neighbor, right? And this was kind of my idea of an offset. That's not the best way to do it, right? So this is doing the offset, kind of, right? So it's going to be a lot easier if we do this as a pre-computation step, like the other guy's implementation does. And I think that's kind of, this is the first implementation I had looked at, so again, this is not maybe the optimal way to do it, but you know, we're homing in on it. So the they're eliminated if they don't match the color. That's just image output. So I was just trying to do something where you blend for anything that's not collapsed, right? If the possible tile set size is not equal to 1, get yourself an average of the color weighted by the number of tiles that still bear that color. So same sort of idea as what the implementation I found was. And that's, again, similar to the original. So I'm not directly copying this or anything. I have a couple of ideas that I've got cleared up based on this guy's implementation. I think a lot of it's going to mirror the way I had been doing it. So this generate and propagate cycle is, propagate and observe pattern. This is where he's actually doing it on the canvas. So blah, 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 blah. And yeah, so process the patterns from the input canvas, or the input portion of the canvas. I'm not very much up on my JavaScript. But basically, yeah, so yeah, create a new WFC model, or create this model, pass this as an argument, which these two classes kind of make sense to roll into one the way I was doing it anyway. And then drop into this render function that's going to repeat, and res, I don't know, whatever, is the result of this step function. And the step function says, all right, observe, propagate. So observe finds the optimal tiles. These are ones that have the lowest entropy. So we go through, define the entropy, and entropy here is the lowest number of yeah, this is weird, but that's basically clearing the array of collected tiles at that entropy. So anyway, your end result is an array that contains all those tiles pushed on. Okay, so you've got, in your observe thing, you've got, all right, so you've got your set of optimal tiles. Those are lowest entropy tiles. They're the closest to being resolved. Okay, so you got none, you're done, right? You have something with a contradiction that is 0 remaining states that are possible. All of the states have been removed in the previous propagate function. So when you drop back in here, you're going to see, all right, well, something's happened that's created this contradiction, and you return -1, and you're done. So, yeah, if neither of these are met, then you're going to pick one of these optimal tiles, pick a random number, grab it, collapse it, and this is another place I don't really like JavaScript because ownership is kind of unclear here. This at oh no, I guess that's fine. Yeah, so anyway, yeah, so go through yeah, so create a vector it's on the board. If it I need to look at operator precedence here too, because is this not of all this, or is it not of this? Yeesh. All right. Should be not of all that, I would imagine. Because yeah, I'll have to look at that more. I gotta look that up. Order of the precedence there. Anyway, so propagate, then looks at this set of updates, pops one off, so it takes the first one, deletes it. Yikes, I hate JavaScript. Gotta be honest with you, this is not. Okay, replaces it with 0, I guess. This function is very strange. Splice is very strange to me. Anyway, yeah, so tile is the tile you're looking at. Looks at right, okay, so at is the wave, right? So that's the superimposed set of all the output tiles that could exist at this location. So this is going to require some more parsing on my part, but the general structure is pretty clear. So like I have like the parsing figured out a little better in this implementation I'm looking at, and he's got everything else figured out a little better than I do. So yeah, and I don't think this is going to continue to be the best way to represent these. I have some JSON output abilities with this engine that I'm working with. I put it together. It's called Not Quite an Engine, because it isn't really quite an engine. It's but it's a so we've got an OpenGL debug callback, GLM types, PNG loading and saving, diamond square algorithm for height map generation. We've got JSON parsing, DRAM GUI, really nice. Perlin noise, tiny OBJ loader, which I'm not using for this at all. This is a very cool algorithm, and that's gotta minimize everything. That's what I use to generate my well, here, let's go to a different workspace. This is what I generated this with. It's made in Veraldo, but the pattern here is the voxel pattern is generated with voxel automata terrain. It's a very cool algorithm. Anyway, I converted it from the processing implementation to C++. I had to find a replacement for Java's big int functionality, which wasn't that hard. Is actually that's another thing that's been added to the the big int library exists as part of the engine too, because just to support that. But it's actually pretty cool because that code, right now I've got this broken out by, this is the engine code, this is where the magic happens, I guess. This is where you write your own code for this setup. So yeah, voxel automata, no, yeah, it is in there, yeah. So big int goes through, well, so here, let's look at the demo. Yeah, that's right. So it takes a literal, or it takes a string, or whatever. And you've got arithmetic operators that are defined for those types. There's big integer, there's big unsigned, there's whatever. You can do bitwise operations with them. Very cool. Yeah, this is a very cool set of functionality to include. So there's that, and then basically everything else comes from SDL. It's the windowing, it's the OpenGL context setup, it's the, you know, it's the whole shebang. And if you want to do audio even, it'll do that. So that's not anything I have been using, except for the one I tried to do an FFT visualizer, which worked sort of, but yeah. I can, here. So this takes and
the best methamphetamine producer that they have anywhere in this part of the Bible Belt. I would have 2 55-gallon drums, and I would pull a lawn chair in the middle, and I would stack Budweiser this high, and I would have 2 titty dancers dancing on the table, stripping and having a good time, and I would start drinking beer, and the mixture would be in here.
Anyway, it was just some MP3, or it was actually a WAV file, because it's a lot easier to load. It's a much simpler file. Anyway, this delightful gentleman has got some things to say about his chemistry experiments, and the in any event, so it's running an FFT on the audio, and the FFT is computed for a sliding window through the data, and then that data is passed in as an SSBO to a shader that then writes it to an image. That image is then used to displace the vertices across the that sort of a plane thing, and basically it's like, I don't know. I'm not sure why one image is allowing the displace, because all that's changing is the image that's being used to displace. But you're seeing the color on it, so it's like, I don't know, there's some inconsistency somewhere that I'm not catching. Both images are treated identically. There's a front and a back buffer so that I can grab from one and write. So basically I'm reading from one and writing to the other each update and then swapping. Keeps the synchronization a lot simpler. But anyway, not to get too far in the weeds there, I blew this whole thing away. I'm not using any of this code. So the angle tonight is to get into re-implementing this. So rules are going to be a new addition, and these are going to be kept as part of the tile. So an overlap rule looks like, okay, all right, so I have some offset. Well, which tiles agree with me here? Let's take a look at how they represented rules. The way JavaScript does everything in a very ad hoc way, I don't care for that much. Probably under tiles pattern. No, it's under the parsing step. Okay. Okay. That is okay. So it's ordered by offset. So there's not that many rules. There's only as many as there are offsets, and that makes a lot of sense, because then when you're collapsing a pixel, you only have to look at ones where the offset matches. Anyway, I think that's a good way to handle it. Yeah, so anyway, this is a vector of tiles that agree at that offset. So that part is going to stay. This neighbor function was how I was doing the offset checking, and I don't think that's not a good way to do it. Yeah, so we'll get into it now. So So all that has is right, so now once I get through this, at this level, I am going to try and apply it to voxels for Beraldo. Right, because if you can look in through and maybe some very small subset of this and define similar voxel relationships up, down, left, right, and your neighborhood then becomes n cubed instead of n squared. But the rest of the logic is fairly well identical, right? So you're looking at offsets between three-dimensional offsets between these three-dimensional tiles. And the same logic could be applied to video, right? So it's, but then that would be pixels before or after the particular frame in time. In any event, the logic transfers over. I don't like how this does the indenting, but no big deal. Yeah, and it's just pattern. Right, yeah. Patterns are what I had been calling tiles. So a tile has a count, a tile has contents, which is not going to be handled like an array like that. So right. Yeah, so that's just ints. Yeah, C++ understands English plurals, right? Yeah. Anyway, so anyway, we gotta have rotates. We gotta have mirror. Let's go ahead and write those. And I think that, yeah, let's see, image. Okay. This is all from last time. So basically, so you load the image, right, and that's using the load PNG functionality. At is going to be just handling this referencing of the one-dimensional array that holds the, right, it's a, the data is just a vector of unsigned characters, red, green, blue, alpha, red, green, blue, alpha, right? So you know the width, you know the height. This function load, right, and that's that. Count colors goes through and says, okay, I know, well, and this is not, I don't know. This is a weird one. I think the way that I'm looking at, yeah, I need to think more about how this is all going to work. But I think that I'm going to have a way to do this. So that's like invalid is like off the board, or whatever, and that's going to be so that it's an incomplete relationship, right? I have a tile there that's, you know, maybe for a 3x3 tile set, you know, and 3, you know, and it's right in the corner, and 3 to the left. Okay, so it's only got 3 on the board, right? So like, say you're looking at like, we'll just do it this way. Where, okay, 0 is off the board, 1 is on the board. Anyway, yeah, whatever. Come on. Keep hitting page down. All right, so I've got these are on the board. Now these would be colored in with the invalid color, right? So that's anyway, we'll get to that. So colors takes this initial. All right, so data. Right. All right. So yeah, you're looking at the image data from the very first pixel is the first, right? Because it's RGB, blah 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 blah. The very first 3 entries in that data array are going to be your first color. Just establishing in that. And I'm not doing any sorting of this. These are just indexed colors. It doesn't. The pattern doesn't really. I don't want to say it doesn't matter, but it's not important for the problems I'm solving anyway. So yeah, okay, so yeah, skipping through in 4s, yeah, so this is the offset, so it's initialized at 4, which means your RGBA, then the next R is at entry 4. So we grab 4, 5, 6, those are RGB, okay. We say we haven't seen it yet, so then we're going to iterate through all the colors. If we've seen it, we've seen it. If we haven't seen it, we push it on the back. So not complicated. This is just parsing the colors, and then we have an indexed palette once this returns. So that part's not super complicated. Anyway, so these rotate functions are going to be, I know the dimension is defined by n, right? So we're just going to use dim. Pattern rather. These are going to be functions of this class so that it takes the local data. Wait a second. Well, it knows n, right? Because it's defined in a global context, so it's not a huge deal. We don't need another variable. I think mirror is going to be a lot simpler. So basically, I do like range-based for loops, but I don't think that this is appropriate. I think the indexing is a lot easier if I just do that this way. Okay, so temp squares. No, we're not gonna screw with that. It'll just be temp dot. Temp dot tile comments. Yeah, all right, we're gonna shorten that. Okay, mirror is going to be we'll just say it's across the x-axis. All right, and then is that right? I think there might be another. Yeah, I think it's n minus 1 because, yeah. And y is going to read. No. Wait, what am I doing? This does it. Yeah. Okay, yeah. Yeah, and I don't need to, but I do like, just for completeness sake, just do this. Cool. So that's all there is to mirroring. You're going to reach across the x-axis and grab the one that is. All right. Yeah, I guess right. So the result then is a mirrored tile. Rotate, not too bad. I think it should just be swapping y and x, or x and y rather. So very similar. So I do kind of get where his logic's coming from in the other implementation. Right, this type of stuff where it's, you know, this size of x, blah, blah, blah. But I just don't like how it's hard-coded and it's not general enough. So I'm gonna write the more general version and we'll do it this way because I think it's just better because then I can support all 4, or rather all 8. Just hit the right keys, I'll be all set. Okay, and that is going to equal. Let's think about this. Well, let's look at it in the context of this other one. So, or does that even make sense? Yeah. Let's draw some pictures. All right. So, just apologize in advance. This is going to look like shit. So, we got our box, say n equals 3. Okay. So, and I do like doing it this way because it's a lot more general than the way I was doing it with it hard-coded. So we're going to do it this way. So the two-dimensional array kind of approach. Yeah, and I can already tell this is the right direction we're looking at. So, yeah. So if we look at it to do a counterclockwise rotation, there's a little bit more to it. Okay. Mirrored rotations are very easy. Because if you look at it, okay, 0, 0, 0, but then it's 2, 1, 0. But if you're going to look at it this way, it'd be 0, 1, 2, but then it's 2, 2, 2, right? So let's think about it. So a rotation would then be so then we're considering these as yx. So then y 0 is x, y. Just keep that on hand. I'm going to draw this out because it's a lot easier for me to think on paper. Okay, so then a rotation one step counterclockwise puts us at Okay, so go through this, then it's the y value becomes n minus 1 minus y. No, so x value becomes related to y. No, the x value is just the y value. Okay, and then the x value screw myself up here. The data is stored in x, 1. Okay. Then I want this information. This is still x. Right, okay, so this is wrong. This is x is used to give you the well, I can test this. It's not, yeah. Just make sure that okay. So I think then this is n minus 1 minus 1. I think that's right. Just to test that really quick. All right. Which one is plus plus? Which one is minus minus? Which one does it return? Yeah, so plus plus I returns the value after it is incremented. I plus plus returns the value before it is incremented. All right, very good. So we got the one we want. Think you're clever, John? You're wrong. Alright, so okay, so we output the first, just make sure it's the space above that. And some space after that. Super important right now. Nice. Where are we so far? No. Duh. Let's go ahead and do that in the constructor. Alright, so resize the data vector for each of the sub-vectors. Resize this as well. Should be fine. All right, 0, 1, 2. Flipping it. Okay, rotation looks good. Flipping. Yeah, it doesn't. Oh, duh. Yeah. Well, in any event, it is distinct, isn't it? Yeah. Well, and it is mirrored, so. No, I don't like that. Why don't I like that? It should be fine. So this time we have a clockwise rotation and we've got a vertical flip. Neither of which is particularly relevant because if you think about it, we're just generating 8 of them. It doesn't matter as long as they're distinct. And I have these two basic operations, right? So this has just been flipped across this center line, the 3, 4, 5 line, right? So this is, if I were to rotate this twice, these two things are not equal, right? Because then it's 2, 1, 0 on the top, 3, 4, or 5, 4, 3 across the middle line, and then 8, 7, 6 across the next one. So yeah, that's fine. So input flipped, rotated, and rotated is rotating this way, this clockwise, and that looks good. Very good. So okay, so we've got our just for fun. No, but whatever. So then we've got the model functions. output tile, and WFC. All right. All right. Anyway, so this is a model function. Okay, so just drop all that. Blah, 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 blah. All right. So this should load an input. Whatever. Yeah. Just yeah. This is pretty much directly from the other one. So I have those input pieces all numbered out. So then I'm just going to do I'm actually going to copy this directly from my old implementation. So it's not num, it's f. Yeah, that's it. Okay. Okay. So load PNG load, right, with right, image in m.in.load. Looking good. Let's make sure this is all going to go smoothly. Let's just go ahead and compile it now. Well, yeah, whatever. Yeah, doesn't matter. Do I not have a model declared anywhere? Kind of would help, I guess. Thought I did. Yeah. Oh, yeah. Helps if you save your files. Still not liking that. Interesting. Should be model M. Model M dot in dot load. Yeah. Yeah. This is engine. Yeah. Model M. M was not declared in the scope. there's one thing right away. It is local to the model, so it's not. Yeah, so that fixed it. Cool. Okay, I've loaded an image. We're good on that. Cool. Okay, go ahead and do make sure we know the colors. Okay. Next is get all the tiles. Then sort tiles. Remove duplicate tiles. What am I calling those? They're overlap rules, I guess, yeah. And this is just the offset and the agrees thing, right? So it's, yeah. Okay, so get all the tiles, not that hard, that's basically okay. Now this one is doing some stupid bullshit. Now at does bounds checking. Oh, I took that out. I'm gonna put that back in. I don't know why I took that out. Okay, so I am going to go back to this representation. I'm going to consider these invalid. So that's an incomplete relationship. Then, so the tile doesn't have to match at those indices. It just has to match places where there is data. So I think that's actually a good way to handle that because that's more general. Cool. Yeah, and that way I don't have to do any bounds checking in the loop here. I can just straight up run through them. It's not a big deal. I think I may actually have that written, so we'll just kind of take a look here. okay, yeah, alright, shit. Got a lot of things already done here. And I'm just pulling this from the previous commit in my old project, so. Now, this has to change. Right, because they're n by n tiles now. It's not general enough to go by the 3, right? So where I had been doing this hard-coded setup, that's not going to work anymore because I have a variable n. Okay. And I really should rewrite my tile dump function because it kind of looks like shit, and it's a very long function. So there's a lot of repeated code, or not exactly repeated, but it's like close enough that I should be able to do something. All right, so blah blah blah. Got my tile temp at data. Shoot. Huh. So yeah, this is one place where that n by n thing kind of throws you, because it's like, all right, what do you do in a situation where it's 2? Okay, there is no center pixel, right? So it's like, So you just go x, y. Shit. I think that's pretty much what it's got to be. Well, because n equals 1 has no meaning. N equals 2 is offset like that. N equals 3, there's a center pixel, but I don't know if it makes sense to use it. Yeah, I'm doing too much of this thinking of it in terms of neighborhoods. It's not really, no real strong relationship between it's not the neighborhood that matters, it's the tile. I'm thinking about iterating through for each pixel, looking at the neighborhood of that pixel. As long as I get all the tiles, I don't need to worry about the neighborhoods. Because the neighborhoods are implicit in that tile data. So, yeah. Yeah, because I guess that ends up just leaving one. There'll be one at the very end. Yeah, there's one at the very end that's in the bottom corner that will be 1 pixel on, and then the rest of the pixels are off. And I actually asked the fellow on Twitter, I asked him good thoughts, if he had any good thoughts on. I told him a little bit of information about my plans, and he said if you are going to run it on large size inputs, consider dropping the rare cases. And so, because there will only ever be one of them, there's a lot of them. There will only ever be one. Well, is it going to constrain anything? Not really. Ugh. That's a weird edge case to deal with. It's not really it's a literal edge case. It's case at the edge. But yeah, fuck it. We'll deal with that. We'll just accept that as a tile, because I don't think it's going to constrain anything, and makes the code a lot simpler. So we'll just go ahead and do that. Right, then the mirror, rotate, blah 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 blah. Yeah. Okay, and now removing the duplicates is alright. So again, I was going into big O notation and shit earlier. This scales with, we'll call it n, but it's kind of n squared, just based on if you're talking about a square image. Anyway, so if n is the number of pixels in the input image, then sorting scales with n. Well, the sorting function is going to establish that, but duplicate tiles is going to be scaling with n squared, because you potentially have to run through the whole vector every time for every entry. It's not n log n, it's n squared. Establishing overlap rules could be, so this will significantly restrict the set of tiles, and then we'll establish the overlap rules. So removing duplicates is going to be yeah, that's the overlaying action. So that scales like crazy. That's kind of like, yeah, like the pre-computation stuff. Like previously I wasn't doing that step, and even just like the part that I was doing, so where it's the tile parse, tile sort, and then yeah, like just the tile parsing really was apocalyptically long for some of these, especially when I rolled in the duplicate removal to the adding of tiles. So each adding of tiles, right, runs through the list of tiles, sees if there's one in there, increments the count. I think it's going to be a lot more efficient. I mean, at least a good chunk more efficient to collect them all. Don't do this checking when you're adding them. Go ahead and do it at the end with it sorted. I'm not exactly sure. I don't know. My feeling is that it's considerably more efficient to have that sorted before you do it. Just a lot less checking. So, sorting the tiles. Let's do some reporting. Let's go ahead and pull that directly from the other implementation. Another thing that I'm going to look at doing is using the JSON thing, and I may have already talked about this, but so using the JSON output to store this model, because this is so expensive, right? This isn't that bad, but then duplicate removal is expensive, overlap rules are expensive for an image larger than a certain size. There ends up being a lot of work. So now, well, let's just go ahead and look at this. Yeah, this is stupid that I did this, but so one of the input, I'll just run through some of the input images. So small, block. Okay, this one's not as small. I'm not sure why it doesn't resize. So you can kind of see some of the sizes. These are pretty big images, and these are not at all representative of the type of input that the guy was using in his thing. So I'm just kind of curious to see what this will do. Hoping to make an implementation that'll work on small images like this guy, right? But then potentially have some ability to operate on images like this. So let's go through them in order. Larger stuff here. The biggest one is 1920 by 1920. That's this guy. So, you know, you zoom way in and you see the pixels, right? And I used GIMP to reduce the color count on all these down to 10, 12, 16, somewhere in that range. So, and I may just be getting dithering patterns out of these things if I do get any output at all. So we'll see. But I think it's going to be a cool experiment in any event, and I'm excited to give it a shot. Right, so then I've got some of these smaller ones that are potentially a lot more reasonable to expect good output from. This needs to be rescaled because those pixels are 4x4 or something. Yeah, and so some of these more recent additions, I kind of gave some more thought to number of input pixels. And some of these have really had the color count reduced to like 6 or 8 or something. So hopefully that keeps the combinatorics and things in check. Need to fix this while I'm thinking of it. Yeah, this would have created a lot of degenerate type things. 5 by 5, wow. Cool. Cool, so these are my proposed input images. And some of these are not at all practical, so we'll get there. But I think some of these more recent ones, like this guy might make some sense. This one, I don't know. And one of the problems that was described in some implementations that I've seen is what's called overfitting, and that we actually saw that when I was screwing around with that browser-based right, when I make this elaborate shape that whatever, I don't get a huge amount of diversity. Well, this one, bad example, but see, because here now I'm getting some diversity in the patterns, right? It's not just everything that looks like this. I'm getting something that looks like a bird, all right, and something that looks like this, something that looks like this. Some of these just isolated red pixels. And this is where the function gets cool. Like, you see this like diversity of patterns that comes from this simple input, and all these are represented in the input, right? Because this stretch of red, okay, that's that stretch of red, and especially for n equals 2, the checking becomes a lot easier too. So yeah, because if you crank that to 3, this particular implementation is kind of a little bit of a mess. But so it gets much slower. And yeah, here we're seeing sort of an overfitting of the input, because this is like, okay, I'm looking at this, and you know, this is directly representative of part of the input, and radically slower. But that has a lot to do with the fact that it's running in JavaScript and things like that. That's interpreted and all that shit. But it is also a lot more checking. See, now this whole thing dropped in as one big chunk because it's, you know, one big collapse like that, and then it's like, all right, I saw a blue pixel, well, all right, I know this, and there's only one sort of set of relationships right here. So as soon as anything in this kind of range collapses, then it's going to see, all right, well, I'm just going to go ahead and redraw that input model. So that's that overfitting problem. So that's kind of maybe what we'll be seeing is a bunch of bullshit as output, but I'm quite interested to find out what I find out. So tiles sorted. Shouldn't take a long period of time. Okay, so long it takes to sort the tiles, how long it takes to do blah, blah. And hopefully this should be in microseconds or milliseconds or whatever, because oh well, I kind of got distracted here, but so like I said, for this large input sample, right, 1920 by 1920, I believe. Yeah, that's what it is. I was able to get the, I let it run until it finished, just because I was curious. But what that produced was a 27 megabyte PNG. Actually, it takes a second to load. It takes wall clock time to load a PNG. It's pretty impressive. Think that, yeah, so 601 by 168,217 pixels. So basically, I established some width in tiles, right? It's like 150 tiles wide or something like that. And I create the tile dump of all the unique tiles, right? Well, this is sorted by count, so we have some up here that are very common. These happen a lot. But then you see, there's kind of an interesting pattern. So there's you start to see these runs become shorter and shorter and shorter, or shorter as they go up, because they're sorted by count, and then below that they're sorted by center color. So these stripes sort of emerge a little bit. But quickly you see these start to stratify in an interesting way. So you've got really, really common ones up here, and then you've got the huge number of more, or of less common ones that are just slight permutations on one another. But yeah, this goes on and on and on, and then eventually these are large ranges. These are just like, okay, I only ever saw one of these, you know, but then there's like just a crazy number of permutations of that. So if we were to go in and look at some of these orange ones, like, you know, these are all distinct tiles that and basically what took so long to generate this, and this was something like 20 something hours. I mean, this is like, it's nuts. It was the n squared big O there, in that it has to check against the whole set of tiles. You know, you're initially generating something like, well, so 3.7 million without the rotations and flipping. So 8 times that. It's, you know, in the tens of millions. And then, you know, you got an n squared based on that. So that's kind of where I'm talking about the input. We're gonna call the pixels n squared just because the image is squared. right? Anyway, but so that kind of starts to look like n squared times n squared. So you're looking at n to the fourth, and so like I said, this explodes quickly, and you know, this may be totally wildly impractical for, you know, what I'm trying to do here, but I'm moving with smaller sets like this, where you can kind of reasonably understand it. Maybe that's something that'll be practical. And again, the set for the flower is only like this. Right? It's only this many tiles that are possible out of that input image. So that's yeah, interesting. And I'm not sure what that means. It may just be that it's slow and we'll still get some interesting output, or it may be it's total bullshit and I'm just going to get white noise out of it. So, you know, it's going to be interesting. Basically, my previous iteration was just producing white noise because I was doing something stupid. And I was actually misusing the function that I thought was really cool, right, with the lambdas or whatever. Without the iterator after, it doesn't do anything. It removes the first that this iterator goes to, which is a real pain in the ass, because basically what this is saying is like, all right, erase one element that is the first of this process. So you're running this whole damn process. Doesn't matter, I guess, that you're running the whole process, but you're only getting the first one because when you look at the erase, right, position, right, if it's one argument, it's position. If it's two arguments, you got first and last, and you iterate from the first to the last. Okay. An important distinction when you're trying to actually get anything done, because this is going to only remove the first, and if you had it remove all of them, it quickly segfaulted. So this was wrong, just dead wrong, and I need to redo it. Anyway. So basically, it was just a whole bunch of runaround, and the only things it was producing were nonsense. Like, well, no, there was one instance where the pattern in the output was a J. So it was like it was communicating with me or something. Anyway, for J for John or whatever. Yeah, so the I thought that was really cool, and I may have an occasion to do it again, but this is actually a good little exercise to understand the capture list and the lambda syntax, because this is so nice. I mean, this is like, the way they've implemented this is just like, ooh, it's really, really nice. I mean, it's just a really, really, really nice little syntax for lambdas. Granted, I haven't used lambdas in other languages, but I am pretty happy with how that works. So, sorting the tiles, not much to that. I do need to write the comparison operator for the pattern. So that's really is not going to be complicated. Right. That doesn't make sense anymore. Right, because there's no center, right? Well, the closest thing we have to a center is, and this is the most general way I could do this because every tile size is going to have if the counts are equal, then we check the 0, 0 cell. Yeah, that's fine. If not, return whether or not it's equal. Okay, cool. Looking good. So then equality, just for shits, we'll go ahead and get that done. This is going to be almost exactly the same as last time. This becomes two-dimensional and not fixed size. Okay. That's fine. So any difference in the data violates equality, drops out with a false result. Yeah. Don't actually need this. Make sure everybody's happy. Tile temp. That is actually useful. Yeah, we'll just go ahead and bring that over. It's not too difficult. So this is just a little string stream I was using to basically at the end of the loop add this kind of thing. And that's a carriage return followed by a distinct tile count. Yeah, cool. Let's declare it up here. Tiles. All right, let's see, where's tiles? It's part of the model class patterns now. we're dropping basically everything that tiles was doing. Yeah, okay. So it's just pattern stop pushback. Okay, I'm just going to sweep through here, fix these. Yeah. Looking good. All right. Okay. Right, so this is processing image 0, which is the flower image. So what we're looking at here is 2,760 distinct tiles. Okay, and that's good. All right, well, shit, yeah, I haven't removed any tiles, so. So sorted. And I'll run this on something bigger so that you can see what that other does. 24 finishes in a reasonable amount of time because it's a small image. And I know that some of the other ones are going to now still too. But we'll see what that looks like. So yeah, ran through, counted it out. Still too fast. Yeah. Oh damn, it's too fast. Yeah. Well, we'll do 21 because that's the one that takes calendar time. Well, it doesn't actually take that long just to parse the tiles, but the removal is the really heavy-duty part. It's still enough that we'll be able to see it. Yeah. So it's counting them out. Blah 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 blah. Runs through, shows you how many tiles. 30 million tiles, whatever we're doing. Yep. Cool. Looking good. sorting the tiles is very simple. And this is, it's probably just faster to have it return the opposite. Especially since the way it's being compared is so arbitrary. But I'm just going to leave it because it's not that big a deal, and this is definitely not the bottleneck. And then you're saying less than is greater than, and I don't want to do that. So, cool. Yeah. All right. So removing the duplicate tiles. This is where you got a real spicy meatball to deal with in terms of time complexity. Go back to this and get the remove duplicates. That is actually better. Okay, we'll do it that way. Good. Patterns. So, right, my intuition is that this is faster. So, yeah. Okay. Let's see what that looks like for not number 21. So, yeah, tiles size, blah, 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 blah. Okay, so it is, yeah, just fix that. this on something that takes some reasonable amount of time. I should check what that is. Okay, so we'll just run it on number 18. Yep. Oh, something's not getting multiplied by 100. Wait. Is that? Whoa, Jesus. Fuck, that's slow. Is that real? %, and it's at 40,000. Wow. Whoa. Jesus. That doesn't make any sense though. 400,000. I over patterns on size, right? That's patterns on size. Times 100. Wow. Wow. Jesus. No, it doesn't make any sense. That's up around 10% removed. What's going on here? Yeah, something's going on here. That's not above board. I'm going to try a smaller input image. This is 300 by 200, and so we'll just try something that's not that big. And so this is kind of where I start to think like, is this at all practical to do it this way? Or am I just kind of looking at this completely wrong? I'm not 100% sure yet, so I'm still working on it. Yeah, so this one is relatively small, like 269 by like 1 something. No, 218 by 133. Now that's not. 203,000. Jesus. Because at 3%, there's no possible way that you've removed more than 10% of your thing. Doesn't make any sense. So I think it's going to terminate it at around 10%. What it's claiming is 10%. I don't know what I'm doing wrong here. Jeez. You can't be removing more tiles than there are tiles. How does that make any sense? There's a lot of repeats, I guess. That's... No, what am I talking about? That does make sense. All right, yeah, because you're iterating through the patterns. Okay, so any repeats, like in the low digits here, it's sweeping through the whole array. Yeah, that actually does make more sense. Still, apocalyptically long period of time to do that process. And that's where we're seeing some trouble here is, yeah. Like, for a small image, like this is the size of the image. That's how long it took to remove the duplicates. 90 seconds. Doing it this way. So there's 60,000 out of those initial 230,000 that are valid non-duplicated tiles. Fuck. Let's try another one. Then I think I'm going to convert the, so that's this one. I'm going to convert the tile dump code to like, I don't know. So yeah, in these low numbers, it goes very slowly, but then, yeah, as you start looking at like 50% done, you're now operating on a list that is at least 50% smaller than your initial list, and probably considerably more than that because you've had at least some tiles removed. So yeah, this first couple percent is the longest, well, the first percent is the longest, and then it gets progressively faster and faster because you're operating on a smaller and smaller list. So I guess this is working. I just wasn't thinking about it exactly right. So yeah, you're accelerating as you go through. Still doesn't look good, I guess, from an observer standpoint. It looks like it's taking forever to do it. Yeah, the time between 0 and 1 is like way longer than, yeah. So after this, what's next? I'm going to do a tile dump. That'll be the model. Right, so the index.png tiles, whatever, yeah. Or probably the other way around. Alright, yeah, so we'll skip that. Okay. Now, oof. Shit. Well, good and bad, I guess. I'm going to have to rewrite this. Shit. Okay. Well, it's not that big a deal. Well, and we should time this too. Is that still running? Jesus. See, this is what I'm talking about. This is so slow. I think we're going to start reporting this soon. There are some very nice utilities in the standard library now. I'm really pretty fond of what they've been doing with that. Especially the random generation is really nice. Chrono, really nice. Stuff with the lambda stuff. I mean, the algorithm header is, oh man. I need to look at, well, wait. Now this is, so this just finished. 434 seconds for an image that size. There's a lot of work to do for, you know, for that. And I fully expect the next part to take a good chunk of that too. Probably equivalent, if not more. Was that right? Yeah. Well, so it's a much smaller list, right? Because we've pared it down to, so there's no more duplicates. So your input size is much smaller to this next stage, but then it is squared again. So yeah, we'll see. Removing, so by shifting the elements in the range such as the way. So this removes, yeah, and this unary predicate thing is, that's the lambda. The, right, this lambda is, and this is wrong. So I don't think I actually ever made a commit with it right, but I did actually figure out how to do it correctly. But I went through that earlier. It's only hitting the first element of that iterator that has the yeah. Anyway, it didn't have the end iterator there, so it was. And the semantics there are a little bit confusing because is it removing? Yeah, the semantics are a little bit weird there. And like I say, this is not super relevant because that's not the way we're doing this anymore. So, okay, tile dump. It's getting kind of late. I think probably gonna wrap this up. Yeah. All right. Getting this in the morning.